So the work I'm going to present has been generated recently in the framework of IMEET, which is Christoph Brabeck's group at the Friedrich Alexander University in Erlangen, Energy Campus, and the Center for Advanced Energy in Bavaria in Erlangen too. So I'm basically dividing my talk in two very different parts. The first one will be about fabricating stable tandem OPVs using rather stable active and interface layers. And the second topic will deal with looking into tracking water diffusion in encapsulated devices. So as mentioned early this morning by Frederick, degradation is a very complex issue, and mostly because it can occur at different locations. It can occur in the active layer, at the electrodes, in the buffer layers. It involves different species at different time scales, which really makes this elucidating what is really going on very, very, very complicated. And one way of certainly mitigating the problem of extrinsic degradation is by using barrier materials that are able to avoid ingress of oxygen and water. And what you see here is three examples where barriers with different water vapor transmission rates were used. And depending on the quality of the WVTR, you can really see that the lifetime of these devices are increased. The problem is really that materials with good water vapor transmission rates in the order of 10 to the power of -4 are kind of expensive and can cost up to 50 euros per square meter. And if you consider that you have a device that has like a 10% efficiency, this would account right away for 50 cents per watt peak in a commercial product, just coming from the barrier material. And often what you really see is that the degradation occurs because the appearance of an S-shape in your IV performance, which is supposedly related to water and interface problems in your charge extraction layers. So let's look at lifetimes from the literature. This will help us to put our work into perspective. And on the right hand side, you actually see the work that was recently presented by Thomas from McKee's group, where you can see accelerated lifetimes in the order of 6 years when using glass-on-glass encapsulation. You are certainly familiar with the work that is presented here, where this is formerly from Konarka, where lifetimes in the order of 1 year in auto conditions. The same happened in this Interlab auto lifetimes study, where lifetimes in the order of 10,000 hours were reported. And recently, the Krebs group even managed to fabricated roll-to-roll printed tandem OPV modules, where the lifetime is, I would say, rather limited, but was certainly probably not in the focus. The encapsulation was probably not the focus of this work, and also it's a very complex structure. So we are very much interested in using the tandem concept for increasing the power output of our organic solar cell devices. And we recently published a work by George Spiropoulos, where we doctor bladed tandem OPVs on flexible substrates, and using laser patterning, we made modules that consisted of 3 different cells with power conversion efficiencies in the order of 6%. So the question for us is, can we make such a complicated structure with many layers involved, with many functional layers involved, that have a very long and relevant lifetime? So this brings me to the first topic of my talk, which will describe stable tandem, the design of stable tandem OPVs. So we designed the tandem cell, which you can see here consisted of ITO, aluminum doped zinc oxide, P3HT, PCBM. P-dot zinc oxide is the recombination layer. Barium hydroxide we used as let's say, a stabilizing interface, as I will show later. And this diketopyrrole thiophene block copolymer, and moly oxide and silver on top. So the idea was to use active materials that can be processed in air. So all of this was processed in air from solution. Only the top electrode was processed from vacuum. And we also tried to follow like common guidelines where we know that these materials are unstable, and try to replace them by more stable materials. For example, we didn't use, or we used P-dot only, tried to use P-dot only in the intermediate layer and replaced it at the top by moly oxide. Parallel to the tandem cell, we also fabricated the equivalent single cells for intimate comparison. So these tandem OPVs are, let's say, not as efficient as the ones I showed before, the modules, mostly because of the use of P3HT PCBM here, but they are medium efficient and useful for carrying out lifetime status. So this is our photo aging setup, and we used, for a specific purpose, we used white light LEDs without the UV component. And the reason being is that we were interested in learning how UV light soaking actually affects the lifetime of this type of devices that requires UV light soaking in order to have full IV performance without S-shape in these curves. So what you see here is an experiment where we did 2 cycles of characterization, and it starts out with the beginning with UV light, and then we measure the performance, and after 60 hours we apply again UV light. You see here the VOC, the JSC, fill factor, and the power conversion efficiency. And you see that the tandem cells are relatively stable, comparable to the single cells, in some cases even more stable. And you see that the VOC doesn't change a lot. What is mostly affected is the JSC and the fill factor. Interestingly, you can see that after applying the second UV light soaking step, the performance is basically recovered. So the first decay basically mimics, the second decay mimics the first decay. And you can also see here this one example IV curve where we measured at the time 0, then after 60 hours, and again after light soaking, and you see the loss in JSC, and the loss in fill factor here. So then we were interested to learn how long does this UV light soaking state actually live. So we run an experiment where we would UV light treat the devices. Then we would keep the samples in the dark and then probe the performance. And you can see that at least for 10 hours there's basically no change, and then there's a quick decay after that time. Again, at the end, we do a UV light soaking step, and you see that the performance is basically fully recovered. And this is typical for devices that really use zinc oxide, and has been observed by other people. So then, from what we learned, we designed a long-term lifetime test where we would probe the devices, but prior to each IV testing, we would UV light soak the sample. And you can see that by doing so, the performance is really very stable throughout 2,000 hours. And if you even extrapolate this data set, you will see that the extrapolated operating lifetime is somewhere around more than 20,000 hours. And we are certainly aware that this is a comparison that is probably not very fair, but because again it uses glass-on-glass encapsulation, and so we think this somehow represents an upper bound of possible lifetimes. It also uses evaporated electrodes. So if you, compared to fully printed devices, there's certainly a big discrepancy, which is to be expected. But it tells us that using the right conditions, using the right materials, very long lifetimes are possible. We think also that one of the reasons why this particular type of device is very stable is the use of barium hydroxide. On this slide, you can see a comparison for P3G PCBM inverted devices, where in one case we used barium hydroxide, which is the red dots here, and in the other case we did not use barium hydroxide. And you can clearly see that in the case where we use the barium hydroxide, the devices are significantly more stable. We are trying to currently figure out what the reasons are for the stability increase using barium hydroxide. And we have some data about it, and what you see here is the dark IV curves, and you see that in the case of barium hydroxide, there's a reduced energy barrier, so electrons can be extracted more easily. On this side, you see that the leakage current goes down, so there's a higher shunt resistance in these devices. And what I didn't show here is that, at least for this system here, we see also considerable increase in the short circuit current, which tells us that there might be a dipole moment at the interface involved that reduces the work function and facilitates charge extraction from that side. We also see from capacitance voltage plots that in the case of barium hydroxide, there is an increase of the built-in potential, which also might contribute to the improved charge extraction in the case of where barium hydroxide is used. So I'm shifting gears now, and I'm going to report on some activities where we are trying to track water diffusion in encapsulated devices, and doing this by imaging techniques. And this is important because from the literature, and this is a report from Belectric, it is known that when there's only oxygen and light involved, that typically what you see is a decrease in short circuit current, while when there's mainly moisture involved, you see a decrease of performance due to the buildup of a barrier and the buildup of an S-shape in the IV performance. So we are very much interested in looking into the effects of moisture and how we can observe that. So we designed an experiment where we have inverted P3G PCBM devices encapsulated, again, glass on glass. This is a typical device performance. We used a climate chamber and a solar simulator to track the performance. And what you see here is the temperature-dependent device lifetime. So you see, again, current, VOC, fill factor, and power conversion efficiency for different temperatures. And while for devices stored at 7 and 20 degrees, there's almost no change. There's a drastic change when the temperature is increased, again, around the glass transition temperature. So 50 and 65 degrees temperature show strong disruptions of device performance. And if this data is extrapolated, we see a shelf life of 20,000 hours for 20 degrees C and somewhere around 2,000 hours for 50 degrees C. So our question is, or was, is this mostly related to moisture or oxygen? And we did an experiment where we would keep the temperature constant and would vary the level of relative humidity. So 20% the black curves and 85% the red curves. And you see that in the case of in the case of 85%, the devices are rather stable. But when the moisture is increased to 85%, the device performance decreases rapidly. Assuming that the oxygen didn't really change a lot, we believe this is really due to moisture ingress and accelerated degradation due to the presence of water in these type of devices. And the fact that JC remains stable, at least in this case, tells us that this might be related rather to an interface problem than to the active layer itself. So we analyzed the data in terms of an Arrhenius behavior, draw linear curves to the data, and plotted then the acceleration factor of as a function of the inverted time. And by doing that, you can extract an activation energy. And we did that for JSC fill factor and the power conversion efficiency. And the activation energy is somewhere between 440 and 470 millieV. In the dark, exactly. So all these measurements actually were done in the dark, and we only varied the humidity. So in assuming that water is really the main cause for degradation, we can associate the activation energy that we measure here to water diffusion in our devices. And similar values have been reported before. In this paper here, I didn't mention the value, but it was somewhere around 350 millieV. So as I said at the beginning, we are trying to observe the ingress of moisture by direct optical means. And what we set up is basically a camera that is driven with lock-in technology, which allows us to really acquire images and in this case electroluminescence to very low levels. For that purpose, we have to either pulse the current or the voltage that we provide to the sample, or in the case of where we apply light to the sample, we have a pulsed light excitation. So we basically did electroluminescence lock-in tomography, thermography, or sorry, not thermography, but lock-in imaging. And I'm also going to show lock-in thermography, where, as I mentioned before, we did either pulse the sample with a pulsed bias, or where we pulse the light source. So in the case of these ELLI images, you can clearly see at the beginning the electroluminescence shining from all the devices shown here. And then as the water goes from the sides into the device, you can see that the electroluminescence decays. And what you see here is the signal from one of these, sorry, whoops, is the signal from one of these. It's actually this pixel here. You can see here again, and we compare the electroluminescence to the darken lock-in thermography and the illuminated lock-in thermography. And in all cases, you can see the same signature, which at this point only tells us that these techniques can be used to track the moisture in this type of experiment. So the question we asked here more is, can we actually use this experiment to distinguish between is the degradation occurring in the active layer or at the interface? And we believe that it's not readily extractable from this type of data. So what we did was we measured the photoluminescence of the same device. So and here in this slide, we are comparing the electroluminescence at the beginning, the electroluminescence after more than 500 hours, and for the same time, we are looking at the PL. And you can clearly see that the signature that you can see from the degraded cell in the electroluminescence imaging is not present in the PL. So the PL actually is stays relatively uniform throughout this time here, where we degraded the sample at again 65-85 in the dark. So this tells us that the active layer actually remains stable or remains unaffected, while the degradation is probably occurring at one of the charge extraction interfaces. We also try to get some understanding of the diffusion in terms of an analytical description. And we basically set up this experiment, as you see here, which this layer is either the OPV cell or the calcium, which is encapsulated into glass. And assuming classical diffusion theory, and what you see here is Fick's second law of diffusion, you can solve this differential equation assuming these boundary conditions here. And this allows you basically to plot the concentration as a function of the position and the time, which is shown here. At the same time, you can, if you plot the position of your waterfront, for example, as a function of t over square root of t, then you should see a linear behavior. And what we did was to analyze a calcium test, which you see here. So this is calcium here. It's encapsulated in the same way as the in the same way as the samples where we took the electroluminescence and analyzed the diffusion. And you can, what is interesting here is that you can actually see that the diffusion that occurs here is in a very similar time scale. So when we plot the calcium test, which is the blue dots, and on top, if we plot also the results from the electroluminescence, you see that they are very close to each other. So this tells us that the water diffusion in the adhesive itself is what determines the cell degradation. And we did this type of experiment where we degraded the calcium for different conditions and different adhesives. And in all cases, we see a very linear behavior, which tells us that this really obeys to this classical diffusion model. We also were able, by doing this, to extract the diffusion constant, which is around 2 times 10 to the power of minus 12 square meter per second. And by using this data set that we extracted from the experiment, we run some finite element simulations, and you can basically see that the way this diffusion occurs is very similar to what we see in the electroluminescence imaging. This also allows us to describe the concentration as a function of the position for different time scales, and we hope that we basically can develop a tool that allows us to analytically predict or to give some sort of prediction for OPV shelf life. With this, I would like to conclude. I hope I was able to show you that by choosing the stable interface materials and stable active layer materials, it's possible to design even tandem cells that have a very long lifetime. From the moisture experiments, it seems that in the devices that we fabricated, moisture is the most aggressive agent and responsible for the degradation. ELLI is a fast imaging methodology to track moisture. This can be done in about a minute, while DLIT and ELLI usually takes longer because the signal is typically much lower. So we are using the diffusion. We are using classical diffusion to describe the diffusion that is occurring in our devices, and we hope to develop a tool for predicting the shelf life of OPV devices. Thank you very much. Of course, there's some acknowledgements.
Yes. Questions? We have 10 minutes before lunch, so I know that you are all hungry and we are in Barcelona, so I understand. I'm also looking forward to lunch, but still.
Very interesting talk, thanks. You showed the study of different temperatures and at the same time different levels of humidity. And it's a bit like unclear for me. Have you looked into really when you heat the sample, is it really the humidity is the same, or you sort of dry a bit the sample and you actually have in reality lower humidity while you have high temperatures? Have you looked into that relationship?
Not in the way you are saying. So what I can tell you is that we use a climate chamber and set it to a certain temperature and certain humidity, and assume that these values are basically correct. But I understand there could be some local heating, I think that's what you are referring to, that might actually make that the humidity locally on the sample might be slightly different, right? Maybe.
Hello. I'm referring to the same test you performed. Did you measure this curve of this different temperature? Did you measure the IV curve at the same temperature? So you aged the different temperatures, but then you measure at the same temperature you measure at the temperature of the aging.
I'm not sure I got your question.
Okay. Now you test you aged your devices at different humidity, but also different temperatures.
Yes, those were two different experiments.
Exactly. Yeah. But then in this experiment, you measure the AV curve at different stage during the aging at that temperature, or you cool down, for example, at 25 degrees for the measurement?
Well, we have, let's say, for the measurement, sure. For the measurement, we have to take it out from the chamber. So
always at the same temperatures.
It's always at room. So when we do the IV characterization, it's at room temperature.
Okay. Also, the same question related to the temperature effect. You measure the degradation at a different temperature, and also at the moisture. So have you ever checked the degradation behavior at a dry condition? I mean, you first have to to make sure that this effect is not due to the only temperature, because when you heat up the device, maybe will increase the degradation as well. So I mean the energy, the active energy might partially due to the temperature effect itself.
So you mean an experiment where at temperature but with dry conditions?
Yeah. Have you ever checked?
We
this
did not
before?
do this.
Yeah.
I believe people did that in the past. We did not do this in conjunction with this type of experiment. So I'm sorry, I can't say a lot about that.
Interesting talk. I have two questions. First question is, the experiments you show with UV light shocking. Yeah, what electron collection layer you use? Is it aluminum zinc oxide or is it titanium?
In the first part with the tandem?
No, in the UV light. When you have this experiment with UV light, so
yes,
you block it and then you let it.
Aluminum doped zinc oxide.
So aluminum doped zinc oxide show UV light shocking effects as a function of lifetime, or when you have it initially show light shocking effect.
Yes.
Initially also show.
Also.
And it's doped. Okay. So this is the first question. Thank you. The second question: why you use barium dioxide? So okay, you said that improve lifetime, and I guess you don't know exactly why. Yeah. What is the thickness of the barium dioxide?
It's 10 to 20 nanometers.
So it's quite thin. So why you use it? Okay, I understand that the lifetime you're not ready to answer the question. Yeah. But
so
why?
We saw it actually started out by seeing very reproducibly that it would increase the efficiency of the polymer of this diketo-pyrrole polymer. That's the way. That's actually how it started out. And then we used it because it gave us high efficiency. We used it in the lifetime tests too, and saw that it also would increase the lifetime of the devices.
One question over here. You had mentioned at least that substituting moly oxide for PDOT would improve the lifetime of your tandem devices with it on top.
So we did not actually test it, but we're expecting that it does from previous experiments that we have seen and from other people in the community.
I think some of us, and maybe Esther can comment on this as well, have actually seen the opposite effect.
Really? Okay.
Where moly oxide is actually quite a bit less stable than PDOT on top of inverted devices.
Okay, that's not what I was told.
Okay, well,
okay.
You should read our paper.
Yeah, we should discuss this, I think, during lunch. With this, I'd like to close the morning session. Let's thank the speakers again.